Hi everyone, and here's our next optimization example. So a similar problem to the last one, just a slightly different figure. Instead of 3 adjacent rectangular fields, we have 2 adjacent rectangular fields. So a total of 200 feet of fencing is available to enclose the fields. What dimensions, and let's just specify specifically the outer dimensions of the rectangle that will yield the largest possible area. So the entire perimeter of this region has to be 200, and we're supposed to maximize the enclosed area. So it's given that, so if you think about the total perimeter for this particular region, it will be, the side is X, so this is also X, this is also X, and the upper side is Y. So 2Y plus 3X is equal to 200, so that's given. And we want to maximize the area, which is the product of the outer dimensions, which is X by Y. So maximize X times Y, the area function. And again, the area function has 2 variables. So something we need to do is we need to, first of all, use the first equation, the constraint equation, to get Y in terms of X. And then we're going to substitute that into the area equation to get that in one variable only. So if you go to that equation, so solve for Y, so 2Y equals, we're going to subtract 3X, so 200 minus 3X, and then divide by 2. So Y equals 200 minus 3X all over 2. Now if you divide that function by 2, you can divide each term by 2. So 200 over 2 is 100. Negative 3X over 2 is simply negative 3 over 2X. So let's take that information now and substitute for Y into the area function. So area equals X times 100 minus 3 over 2X. And at this point, before we differentiate it, let's go ahead and simplify it by distributing X. So 100 times X, which is 100X, and then minus 3 over 2X times X is minus 3 over 2X squared. Now that we have our area function in one variable only and it's in simplified form, to find maximums or minimums, as is typical in this section, we're going to take the first derivative and set it equal to 0. So let's differentiate this function with respect to X. So derivative of 100X is 100, and derivative of negative 3 over X squared, you can bring the 2 down and 2's will cancel. It'll be minus 3X. So set the whole thing equal to 0 and solve for X. So you can add 3X to both sides and divide by 3. X equals 100 over 3. So remember, that's only one of the dimensions, and to get the other one, we need to take that and go back. And here we have Y equals, let's go to that equation and plug in X equals 100 over 3. So Y equals 100 minus 3 over 2 times X. So 3 over 2 is there, and instead of X, I'm going to bring in what we just found, which is 100 over 3. And you'll be able to simplify that a little bit because the 3's can be canceled, and 100 over 2 is 50. 100 minus 50 is 50. So here we have 50 feet for Y. And if they say, what is the largest possible area you can create using the limited amount of fencing available? So largest possible area equals, you just multiply the 2 dimensions because area equals X times Y. So maximum area that we can create using the fencing is 50 times 100 over 3. So that's 5,000 over 3, or 1,667.67. And the units, if everything was in feet, this will be square feet. So this is the largest area we can enclose with the 200 feet of fencing available. And how do we check to make sure that we didn't need to find a maximum and not a minimum of the area function? So take the second derivative. Since area was 100 minus 3x, a prime was 100 minus 3x, a double prime is going to be just minus 3. And that is a number always less than 0, no matter what X is. That tells us it's concave down everywhere, and the point we found indeed represents a maximum of the area function. Now the checking, I'm not going to ask you to do for every single problem. It's a good habit to do it, but at least for one question, be prepared to show that level of work. For the other ones, I'm just going to leave it up to you to show the work for the checking process. Okay, so I'm going to do one last fencing problem. I really feel like if you get strong with those, you understand the technique, the steps, the logic behind optimization, it forms a very good transition towards the other types of problems. So if you get really, really good at one type of problem, it's easier to build on the other types. So I'm going to do one more example. And so for this one, we have fencing on 3 sides of a rectangular field, but on the 3rd side, there is a wall, and we don't need, rather on the 4th side, there is a wall, and we don't need fencing on that side. And we're given that 20 meters of fencing is available to enclose this rectangular shape, where one side will be the wall and the other 3 sides are made up by the fence. The question is, what is the largest area that can be enclosed? So once again, we are maximizing the area enclosed by this rectangular region. So maximize area, which is x times y. And given the sum of all the sides, in this case, there's only 3 sides to this fence, right? It's y plus x. That is 2y plus x. So that is given as 20. 2y plus x is equal to 20. And from there, we know we're going to have to solve for one of the unknowns. And you could really solve for x or y, but the easier one to solve for, it looks like x. So for this one, I'm going to solve for x. So x equals 20 minus y. Just know that you could have done the same problem by solving for y first. And then, you know, you're going to get the y first. You can go back at the end of the problem, come plug it in and get x. So it can be done either way. I'm just doing a convenience here. It was easier to solve for x. That's what I did. But no matter which one you solve for first, you're going to have to go back to the area function and put that in there. So you end up with area in one variable only. So if x equals 20 minus 2y, so we're going to go back to the area function, and right there, we're going to enter 20 minus 2y for x, and don't forget to multiply it by y. So 20 minus 2y times y is area. And as we did with our other examples, it's a good idea now to multiply it out, simplify your area function, and then set the derivative equal to 0. So in this situation, distribute your y, you get 20y minus 2y squared, and then take the derivative. So you're going to have 20 minus 4y is a prime, and set that equal to 0. So when we solve this equation for y, we're going to get 20 equals to 4y, and then divide both sides by 4. So 20 equals 4y, divide by 4y equals 20 over 4, or 5. And here everything was in meters, so y will be in meters. So that's one of the dimensions, right? Let's go back to this equation and also get x from there. So if y is 5, 2 times 5 is 10, 20 minus 10 is 10. So x is equal to 10 meters. So these are the dimensions. So it'll be 5 on the sides, and the longer side will be 10 meters. And what about if they say what is the largest possible area that can be enclosed with the given amount of fencing, with one side being a wall? You just multiply x times y, so area will be 50 meters squared. And if you want to check, so just take the second derivative, which is negative 4. Once again, it's negative, and just like we expected, the point we found indeed represents a maximum. You might say, what about, you know, some minimization problems? Really, it's going to be the same exact process, but at the end, when you do a double prime, in those questions, you're going to find that you get a positive answer, which means it's concave up, which in those questions, you're going to verify that you actually found a minimum. If you're doing everything correctly, you know, when you're looking for a maximum, you're going to end up finding a maximum. And when you're looking for a minimum, you're going to end up finding a minimum. For the most part, there are some very tricky examples about that, but I did not add one of those to your assignment set, so you don't have to worry about those. Okay, so now let's do one more example. This time we're going to use a box. So we've done several examples involving rectangles and fencing problems. So now we're going to do what is known as the length plus girth problems. And here is one of them. Actually, right here. Okay, so here it is, and our next problem on optimization, known as the length plus girth box problem. So the typical question will ask you to maximize the volume of a box with the given criteria, given restriction that the length plus girth must equal a given number. In this case, length plus girth equals 120. First of all, what is it that they mean when they say girth of a box? And here's a picture right here. Girth is the perimeter of the cross section. So if you were to tie a rope around this side, you see right here, and then see how long that rope is, that would be girth. In other words, in our box right here, if you were to add up these four sides, so you tie a rope around those sides and then see how long it is, or literally add up these four sides, that's your girth. So for this example, if this is x, this is x, this is y, those are the dimensions. Well, if this is x, right across from that is x, and if this is x, right across from that is x. So basically this is a square cross-section box, and girth is simply the sum of all those four x's, which is 4x. So when they say length plus girth must equal 120 inches, so given that length plus girth of a box with square cross-section is 120, then we can say that if the length is y and the girth is 4x, y plus 4x is equal to 120. And notice for this question, they mentioned that it was a square cross-section, and that's why I was able to select x by x on this end of the box. And we are, again, trying to maximize the volume with that restriction. So we're going to maximize volume of a box. And what is the volume of a box? Is length times width times girth. Because two of the dimensions are the same here, is x by y. It's x times y. In other words, x squared times y. Now, what is that volume equal to? We don't know because they didn't give it to us. We're trying to maximize the volume, right? We're going to try to find dimensions when volume is maximized. So this is not equal to anything. So one of the common points of confusion I find is that sometimes students will let this be equal to 120. But if you read the problem carefully, you will see the volume is not 120. It's the length plus girth that's 120. And we're trying to maximize the volume. So I would always recommend write down next to the quantity you're trying to maximize or minimize, because that will help you focus that this is your objective function. This is the one you need to get in one variable only. And this is the one you're going to differentiate and set it equal to 0. So once again, there are two variables in there. So I need to go back to this equation and get one variable in terms of the other. The one easier to solve for is y. So I'm going to solve for that. Y equals 120 minus 4x. And use that information and plug it in here for y. So now we have volume equals x squared times 120 minus 4x. Now from this point forward, the process is really very similar. So it would be a great idea, I think, for you to pause the video here, see how far you can go, and then come back and check your work. So I will distribute this. Now here's my important question to you. Should I be setting this equal to 0? And the answer is not yet, not the volume function, right? What should I be doing first? Take the first derivative of the volume function and set that equal to 0. So we're going to set v prime equal to 0 to find the points on the volume function where slope might be horizontal. Therefore, we're going to find the candidates for maximums and minimums. So take the derivative first, 240x minus 12x squared. Then let's set the whole thing, the derivative equal to 0. And to solve for this one, we're going to need to factor it out. I'm going to take out a 12x from both of the terms. That will leave us with 20 minus x equals to 0. So that tells me either x is equal to 0 or x is equal to 20. And clearly you cannot have a box with 0, one of the dimensions being 0. So discard that one. Just use x is equal to 20. And the units for this problem were in inches. So that'll be 20 inches. And once we have x, let's go back to one of our equations from the top, such as this one. Y equals 120 minus 4x. So we can also get y. 120 minus 4x. So of x, I'm going to put 20. So 120 minus 80. So that'll be 40 inches. Now, remember that we are getting the dimensions of a box. So you cannot really just say x by y. It should be like length, comma, width, comma, height. So the dimensions for the largest box that we can create with the given restriction on the length plus girth. So it should be x by y. So 20 inches by 20 inches by 40 inches. And if you multiply all of those together, you will get the maximum possible volume that you can create with these dimensions. So that'll be 16,000, and units will be cubic inches. Maximum volume that we can create. And how do we go about checking this answer? So go from v prime, take the derivative of v prime to get v double prime, and you're going to find that you get 240 minus 24x. Now notice this one has an x in it, right? So that means go ahead and plug the x that we claim to be the maximum for the volume function. So take that x value and plug in here. And really the only thing you want to show is the result positive or negative? So if you plug in x equals to 20 here, so 240 minus 24 times 20, that's going to be negative. And that's really all we need to know. The numerical value doesn't matter that much. So it turns out to be negative 240, and it's a number definitely less than 0. So that means the function is concave down. Once again, the point we found indeed points to a maximum of the volume function. So that's our quick check. Okay, so I'm going to give you one more length plus girth problem, but this time I'd like to give you the statement and have you set it up, and I'm just going to show you the results and not necessarily go through the whole solution. So please take a look at this question. Very, very similar. The only difference is length plus girth is 104. So can you take this problem, follow it through from the beginning to the end, and then in a few moments, please come back to check your answer. Okay, I hope you took a moment to solve the problem, and now you're coming back to check the results. So this is a very similar question to the last one. We are maximizing the volume of the box because it's a square cross section is x by y. So the volume is x squared times y, and it's given that length plus girth, or y plus 4x, is equal to 104. So from there we can solve for y, 104 minus 4x, substitute over here. So you're going to have x squared times 104 minus 4x as your volume function in one variable only. From there, don't forget to distribute it first. So 104x squared minus 4x to the third. And then you'll be differentiating it and set equal to 0 to locate the maximums of the volume function. So differentiate 208x minus 12x squared is equal to 0. From there, go ahead and factor out 4x from both of these, and you're going to be left with 52 minus 3x. So again, you get x equals 0, but that's the trivial solution. The real solution that we're going to use is when you set 52 minus 3x equal to 0, and x is equal to 52/3, or 17.33. And the units are inches once again. So that'll be in inches. And once you get x, you can go back over here and substitute x value here. So 104 minus 4 times 17.33 will give you the y value of approximately 34.67. And don't forget, when you leave your answer, it should be x by y. So 17.33 by 17.33 by 34.67. And the largest volume, you multiply the 3 dimensions. And don't forget, for checking purposes, you would take the second derivative and substitute x in there and show that the second derivative is indeed negative. Okay, so with that, we have done 2 box problems and 2 fencing problems in this segment. And in the next one, we're going to try a few different variety of optimization questions. See you next time.